Welcome to the Deep Dive. This is where we try to cut through the noise, look at the research, and get you up to speed on complex subjects fast. Today, it's a really fundamental one, magnetism, and the incredible power of electromagnetism.
Yeah.
Our sources are pretty broad. They cover basic physics concepts right up to, well, complex uses in industry and medicine.
That's right. And when you think about it, it's this invisible force, isn't it? It governs tiny particles, but then it also shields the whole planet.
Wow.
So yeah, the sources give us a good structure. We start simple with the basic rules and then scale up to see how it impacts, well, everything. The goal is really connecting those dots.
Okay, let's start small then. The everyday stuff. We've all played with magnets. Seems simple. North Pole, South Pole.
Right.
And the rules are fixed, right? Attraction, repulsion.
Absolutely. It's like the most reliable thing. Opposite poles attract, like poles push each other away. North seeks south, north repels north. Simple mechanics, yeah, but it's all driven by some really complex quantum stuff underneath.
Okay, and here's where it gets weird, or at least different from electricity. You can isolate a positive charge, a proton, or a negative one, an electron. But our sources are clear. Magnetism. It doesn't work like that.
No.
If I snap a bar magnet in half, what happens?
You've just done the classic physics trick. You haven't isolated a North Pole at all. You've just made two new, smaller magnets, and boom, instantly, each one has its own North and South Pole. The idea of an isolated pole, that's a magnetic monopole. And yeah, the sources really stress this. People have looked, theorized, but they just don't seem to exist on their own in nature.
That's crucial, though, isn't it?
Yeah.
Electricity literally separates charges. Magnetism demands pairs. It's a fundamental difference.
It really is.
So if we can't isolate a pole, where does this pairing force actually come from? What's the source?
Movement. It all comes down to moving charged particles. Fundamentally, magnetism arises from electrons moving inside atoms. That includes them orbiting the nucleus, like tiny planets, and also their intrinsic quantum property called spin. You can almost picture each electron as a tiny spinning charge.
A spinning top.
Exactly. And if you have charge that's moving, you get a magnetic effect. That's the key.
Right. But we're talking tiny, tiny effects from single electrons. How do we scale that up to, say, a crane magnet lifting a car? How does that happen?
Well, you need teamwork. You need to get those tiny effects lined up. And that brings us to the structure inside the magnet. We need to talk about magnetic fields and, importantly, magnetic domains.
Okay, the field first. That's the area around the magnet, right? The invisible influence?
Yep, the environment.
We can't see it, but, iron filings show it. They make those patterns, those curves.
Exactly. Those curves are the magnetic field lines. And a key detail from the material is that these lines are always closed loops. They always loop around. Always. They come out of the North Pole, travel through space, go back into the South Pole, and then continue through the magnet back to the north. They show the direction and strength of the force.
Okay, loops. Got it. But the real difference between just a lump of iron and a strong magnet is internal, right? That's the domains thing.
Precisely. And this mainly applies to what we call ferromagnetic materials. Think iron, nickel, cobalt.
Okay.
Imagine the inside of that metal. It's got these tiny microscopic regions called domains. Inside each domain, billions and billions of atoms have already lined up their magnetic moments. Their electron spins are pointing the same way.
Like tiny magnetic neighborhoods, all facing the same direction within their little zone.
Perfect way to put it. Now, in a regular, unmagnetized piece of iron, these domains are all pointing in random directions. They cancel each other out.
Chaos.
Total chaos. No overall magnetism. But if you bring a strong external magnet nearby, or rub it,
You give them orders.
you basically shout, "Attention!" The domains rotate and snap into alignment as much as they can with that external field. Suddenly, they're mostly pointing the same way.
So all those tiny fields add up?
Exactly. Billions of them. And that's when the whole piece of material becomes a magnet. That internal alignment is the secret sauce.
That makes so much sense. Okay, so now we connect that internal structure to electricity. This is where the engineering power really kicks in, right? Like electromagnetism.
Yes, because it all comes back to those moving charges we mentioned.
Right.
The huge breakthrough, Ørsted's discovery, was realizing that moving electric charges create magnetic fields. Simple as that. Run a current through a straight wire.
And a magnetic field just appears.
Instantly. Pops right into existence around the wire in a circular pattern.
Okay, a circular field around a wire isn't usually that useful, though. How do you make it stronger or more directed?
You coil the wire, wind it up tight into a helix. That's what physicists call a solenoid. Right. The solenoid takes the field from each little bit of wire and concentrates it, stacks it up along the middle, inside the coil. Now it acts just like a bar magnet.
Okay.
But crucially, it's one you can switch on and off with the current.
And then to really boost it, you use the domain trick again. Stick a piece of iron inside the coil.
Exactly. You put an iron core inside the solenoid. The magnetic field from the current instantly forces those domains in the iron to align, just like we discussed. And that alignment massively amplifies the total magnetic field. That combination coil plus iron core, that's your electromagnet.
The workhorse.
Absolutely. Lifting scrap cars, ringing doorbells, relays, speakers. They're everywhere.
Being able to control the strength of electricity is just huge.
Yeah.
And the sources push this even further, right, to superconducting electromagnets. Why is superconducting such a big deal here?
Resistance. It's all about resistance. To get a really strong magnetic field, you need a huge electric current flowing through that coil. But in a normal wire, pushing that much current generates a ton of heat because of electrical resistance. It melts, or at least it limits how much current you can use.
Right.
Superconductors, though. When you cool certain materials down to incredibly low temperatures, near absolute zero, their electrical resistance just vanishes completely.
Like zero resistance, so you can push massive currents through them.
Almost unbelievable amounts of current, with no energy loss as heat.
Wow.
And that means you can generate magnetic fields that are just staggeringly powerful, hundreds of thousands of times stronger than regular magnets. It opens up crazy possibilities.
Like maglev trains,
Yeah.
using these fields to actually lift the train.
Yep. Levitation. The powerful magnets repel magnets on the track, lifting the whole train, eliminating friction. That's how they get those incredible speeds, over 600 kilometers an hour. And that same technology, that immense field strength, is also the heart of MRI machines in hospitals. Magnetic resonance imaging. We'll come back to that.
Okay, let's zoom out now. From the lab, the junkyard, the train, to the biggest magnet affecting us daily, Earth itself. We call Earth a giant magnet, but the sources say it's not like there's a huge bar magnet buried inside. So what's going on?
Yeah, that's a common misconception. It's the planetary dynamo effect. Deep inside, Earth has a solid inner core, and around that, a churning liquid outer core made mostly of molten iron and nickel.
Liquid metal.
Moving.
Constantly moving. Convection currents plus the planet's rotation keep this molten conductive fluid swirling around.
And moving conductor, moving charge.
Exactly. You've got this vast churning electrical circuit deep underground. It generates enormous electrical currents in the outer core.
And those currents create the magnetic field.
Precisely. It's like a giant self-sustaining electromagnetic generator powered by the Earth's internal heat.
Amazing. So when my compass needle points north, what pole is it actually pointing towards, magnetically speaking? Good question. It's pointing towards the geographic North Pole region, which we call the magnetic North Pole. But magnetically, it's actually a South Pole.
Because opposites attract. The north end of the compass needle is attracted to it.
Exactly. So the place we call magnetic north is technically the Earth's magnetic South Pole. It's a bit confusing.
And they're not even in the same place, the geographic and magnetic poles.
Nope. Right now, they're about, 1,800 kilometers apart? And that magnetic pole is constantly wandering.
Wanderings.
Oh, yeah. The field isn't static at all. The sources confirm it changes all the time. Its strength fluctuates, its direction drifts, and historically, it completely flips.
Pole reversal. That sounds dramatic.
It does. The last big one was around 700,000 years ago, according to the sources.
Wow.
And the geological record shows it's happened many, many times throughout Earth's history. The field weakens, gets unstable for a while, maybe multiple poles appear briefly, and then it flips and settles down with reversed polarity.
But why is this field even important? Why do we care if it flips?
Protection. Its main job is acting as a shield.
Our planetary defense system?
Pretty much. It deflects most of the dangerous, high-energy charged particles that constantly stream from the sun. That's the solar wind and also cosmic rays coming from deep space.
And without it?
Those particles would strip away our atmosphere over millions of years. Mars probably lost its atmosphere that way after its magnetic field died.
So where does all that deflected energy in those particles go?
A lot of them get trapped. They're funneled by the magnetic field lines into huge donut-shaped zones surrounding Earth. These are the Van Allen radiation belts.
I've heard of those. Discovered back in the 50s.
1958, yeah. They trap these charged particles, holding them there until they eventually leak out or interact with the atmosphere, mostly near the poles.
And that's when we get the light show. The auroras.
Exactly. The aurora borealis up north, aurora australis down south, when those trapped particles spiral down along the field lines near the poles and slam into gases in the upper atmosphere.
They excite the gas atoms.
Yep, excites them, makes them glow those amazing colors. It's literally the visual evidence of our magnetic shield doing its job.
Incredible. Okay, let's wrap up by looking at how magnetism affects life itself. Biomagnetism sounds pretty sci-fi.
It does, but it's real. The sources point to certain organisms, specific bacteria, sea turtles, definitely migratory birds like pigeons. They've evolved to use Earth's magnetic field.
For navigation, how on earth do they do that?
They seem to have a tiny crystals of a magnetic mineral called magnetite. It's basically iron oxide inside their bodies, possibly in their brains or beaks.
Like little built-in compass needles.
Essentially, yes. These magnetite crystals align themselves with the Earth's magnetic field lines. This gives the animal a sense of direction, maybe even altitude or location. It's hardwired navigation using physics.
Nature is amazing.
Okay.
Okay, finally, let's loop back to medicine and those super strong magnets we talked about. MRI, it's not just a big magnet, is it? How does it create those incredibly detailed pictures inside the body?
Right, it's clever. It uses that quantum spin property again. The powerful superconducting magnet forces the protons in your body, mostly the ones in hydrogen atoms, because we're full of water and fat.
Okay.
It forces their tiny magnetic fields to align with the main strong magnetic field, like trillions of tiny compass needles snapping to attention.
All pointing the same way.
Mostly, yeah. Either parallel or anti-parallel. Then the machine sends in a quick pulse of radio frequency waves.
Like a radio signal.
Exactly. And this RF pulse has just the right energy to knock those aligned protons out of alignment. It excites them.
Just a little kick.
A little kick. Then the RF pulse stops, and the protons naturally relax back into alignment with the main magnetic field.
They snap back.
And as they snap back, they release that extra energy they absorbed, also as a faint radio signal. And here's the clever part. Different tissues, bone, muscle, fat, fluid, have different amounts of water, different environments for those protons, so they relax at slightly different rates and give off slightly different signals.
So the machine listens for those different signals.
Precisely. Sensitive detectors pick up these faint radio signals coming from different parts of the body. A powerful computer processes all this location and signal strength information and builds up that detailed cross-sectional image.
Wow. What an incredible journey. We started with the tiny spin of an electron and ended with harnessing that same spin using massive machines to see inside us.
Yeah.
We've covered the basic rules, building electromagnets, Earth as a dynamo, even birds navigating.
It really shows how magnetism isn't just some abstract force. It's dynamic, it's essential on every scale, protecting the planet, shaping its geology, guiding life.
So thinking about that bigger picture, we know the Earth's field is shifting, weakening maybe, and has flipped entirely in the past. What happens next time?
The sources say the field doesn't just switch off during a reversal, but it likely gets much weaker, much more complex, maybe multiple poles. So think about this. What could a prolonged period of, say, magnetic instability mean for our atmosphere? For those Van Allen belts? For everything that relies on that shield? Something to keep digging into.